Welcome to lecture number 6. This will be the last lecture about DC circuits. That means that in a few minutes you know everything to analyze circuits, and for the rest of this trimester you will only expand your knowledge for AC circuits and transient effects in circuits. But the most essential things will be done in a few minutes. Today I will just show you some more principles and definitions. So we will talk about the operation point. I will show you how to handle nonlinear elements. I will show you what maximum power transfer is, and we will talk about the principle of superposition. Okay, let's start. Let's begin with the operation point. Okay, we discussed practical sources. And you know that when you have a current flowing out of a practical source, then there will be a voltage drop at its clamps, and then the output voltage of this practical voltage source will be calculated like this, and therefore we have an output characteristic curve, and it looks like this. Okay, what we haven't discussed, but it's very easy, is what is the characteristic curve of a resistor. When a current flows through a resistor, you will have a voltage drop, and the voltage drop will follow Ohm's law and be calculated like this. And if we draw this characteristic curve, it's just a straight line. Okay, and these two lines here, these characteristic curves, say that the blue one, that our practical voltage source can only have pairs of voltage and current at its output clamps that are on that line. And the red line says that our resistor can only have pairs of current and voltage that are on that line. And if we connect the source and the resistor, our two elements are connected, and now they have to find a common voltage and a common current. And you see there's only one point where both characteristics are satisfied. And we call this point operation point, and if we do it in a graphical way like this, we can find the current and the voltage in our system in a graphical way. Okay, if we have a linear resistor, it might be easier and quicker just to calculate with our equations. But if we have a nonlinear element, it might not be easy to calculate anything. It's always easy when we have linear equations, but nonlinear equations are a special type of mathematics and we don't want to use it here. So if we have a nonlinear element, its characteristic curve may look like this. And if we connect this nonlinear element to our source circuit, then again we can find the operation point in a graphical way and find which voltage and current is here at our load. So please, when you have a nonlinear element in a circuit and the output characteristic curve is given, forget calculating anything with that. When it's in a bigger circuit, then transfer the rest of the circuit into a practical source, draw the characteristic output curve of that source, and find the operation point with your nonlinear element. Never try to calculate with nonlinear elements in this class, okay? Okay, let's talk about maximum power transfer. When we have a practical source, you remember we discussed that a battery is a practical source. And Now is the question, how much power could we get out of this battery or out of our practical source? Okay, let's have a look. If we connect a load resistor, then a current would flow and we would have a voltage drop, and we want to maximize the power this load resistor consumes. Okay, let's say our resistor has a characteristic curve like this. And we know that the power is the voltage multiplied with the current. So if we look here, we see the operation point, and then the area between the axis and the operation point is the power of the resistor. It's just the current multiplied with the voltage. So we can just discuss this in a graphical way. So this is, the resistor will consume power. Let's discuss another one. It could be a resistor like this. And here we have a greater voltage at the operation point, but a smaller current. And as I've drawn it, maybe the power would be the same. And now let's think about how we could maximize the area of our square there. If we have an optimized load resistor, then our area would be as big as possible. And if we do it in a graphical way, we find out that our current would be half of the short circuit current of our source, and the voltage would be half of the open loop voltage of our source. Just to complete our diagram, this resistor would be smaller and this resistor would be bigger. But which value has our RL opt resistor? Yeah, it's quite easy. We can calculate it with Ohm's law, because we see when we have the voltage drop of U0 half, the current IS half flows. Therefore, we can use Ohm's law. And you see we get rid of the divided by half in counter and denominator. So it's just U0 divided by IS. Wait a minute. We had exactly that expression when we discussed our sources. This is an expression for our inner resistance. And that means when we have a given source, we can get the maximum power out of it if we connect a load resistor which is as big as the inner resistor of our source. And we could also calculate, if we have a source given, which maximum power we can get out of it. We know that at our load resistor we have the voltage U0 half. We take that a square and divide by RL opt. But RL opt is the same as Ri, and therefore we can rewrite this expression, and our maximum output power of a source is U0 squared divided by 4 Ri. I prepared a simulation for that. What we see here is a practical voltage source. So you see the open loop voltage is 10 volt, the inner resistance is 10 ohm. Okay, and here is a load resistor, and this is an adjustable resistor. We can change its value here. Okay, and here is power meter. You see that it measures the current. So the current flows through our power meter, and it also measures the voltage. So you see we measure the voltage here and here. Okay, and now our load resistor is turned to a value of 2 ohm. So we have a load resistor of 2 ohm and an inner resistor of 10 ohm, and the power consumption here at our load is 1.4 watts. And now I will change the value of our load resistor. So have a look here at this value. This is our resistance in ohm. And also have a look here at our power meter. And now we want to find the value for RL, where the power consumption in our load is at the maximum value. Okay, so I will start here, and you see if I increase the resistor value, our power increases too. Okay, now we are here at 10 ohm, so this should be the maximum power transfer. So if our theory is correct, the power should decrease now when I increase the load resistor. So let's go on. You see, it starts decreasing. Okay, so we've seen that we have really at the condition for maximum power transfer, when our load resistor has the same value as the inner resistance of our source, we have the maximum power in our load. And if the load resistor is smaller or bigger, then we have a smaller power consumption. Okay, this optical impression of the maximum power was quite nice, but you want to become engineers. So let's calculate it. We have our circuit here, a given practical voltage source and a load resistor. And we want to find out at which value for the load resistor we have the maximum power consumption in it. So let's start with the current here. It's just Ohm's law. We have an ideal voltage source U0 and a total resistance of Ri plus RL. Okay, and we know that the power in the load will be I squared times RL. Okay, we can combine these two equations and get to this. Okay, what do we do now? We are looking for the value of RL that maximizes the power P. Okay, let's have a look at our equation for the power. The power is in dependency of the open loop voltage, of the inner resistance, and of the load resistance. And we say now that we know the source. That means U0 is fixed and Ri is fixed. And that means that our function is in dependency of RL. And now we want to find the maximum value of this function. How do we find maximum values of functions? We take the first derivation, set it to 0, and there we have a maximum value. It could be a maximum or a minimum value. We already have seen in our simulation there's only one maximum value. Okay, we want to find the derivation of P by RL, and that should be 0. It's a bit inconvenient here. Our equation for P has RL in the counter and in the denominator. So we want to derive a function where we have one function divided by another function. Okay, but maybe you remember from your mathematics class, if we have such a situation, there is an equation for it. Okay, and here our function u would be, in our case, RL. And our function v would be the term in brackets and square, so the denominator of our function of p. And now we have to derive u and v. This leads to 1, and this here leads to 2 times Ri plus RL. Okay, and now we have everything together and we can write the first derivation of our function, and that should be 0 to find the maximum value of the original function. Okay, if we have a function and it should be 0, it's enough if the counter is 0. Okay, and we have two terms there and a minus sign between them, and that means if the two terms are identical, it leads to 0. Okay, and here you see we can divide by the term in brackets, so we get rid of it on the right side and we lose the power of 2 on the left side. And now we can rearrange this equation and it leads to RL is RI. So please remember, when you have a given source and you're asked to find a load that consumes the maximum possible power, then you need a load resistor which is as big as the inner resistance of your source. So, and now the last point for today, the principle of superposition. We have here a circuit with more than one source, and we want to calculate any voltage or any current in it. Let's say we want to find this current here. And the principle of superposition says that if we have a circuit with more than one source, we can calculate or we can find any voltage or current in the circuit by turning off all the sources but one. And then we calculate the voltage or the current we are looking for. After that, we deactivate all the sources again and switch on another one. And again, we calculate the voltage or current we are looking for. And we go on until we made it for every single source. And in our original circuit, we can calculate the value we are looking for by adding the values from our partial solutions. I will show you how it works. So we have here a circuit with 3 sources, 2 voltage sources and a current source. Okay, and now I deactivate 2 of them. You see, the first voltage source is still in it. The ideal current source became an open circuit and the ideal voltage source became a short circuit. And now we want to calculate this current. I call it I prime. Okay, let's have a look at the circuit. We have a voltage source of 5 volt, and from the point of view of the voltage source we see the 100 ohm resistor, and in series are 2 50 ohm resistors in parallel. That means they behave like a 25 ohm resistor. So our voltage source sees a resistance of 125 ohm. We can calculate the current, and then this current will split and flow through the 2 50 ohm resistors. That means our I prime is half of the source current, and if you calculate it, this leads to 20 milliampere. Okay, but this is not our final solution yet. We have to deactivate all the sources, and now we activate the current source. And we calculate this current again. We can use our current divider rule, for example, and this will lead to a current of 400 milliamperes. And in the end, we deactivate all the sources, and now the third source is switched on. Again, we calculate this current. This time I call it I prime prime prime. And yeah, it's the same thing as in the first case, but the resistor values differ from the point of view of the source, but it will lead to 40 milliampere. Okay, and now we go back to our original circuit, and now we know that the current we are looking for is just the sum of our partial results. So that means our current here is I prime plus I prime prime plus I prime prime prime, and it leads to a current of 460 milliamperes. So, and here I want to show you our example in our simulation program. We have here our original circuit, and below we have our circuit 3 times, but in every sub-circuit only one source is activated, the others are deactivated. I used these red circles here to show you where the original sources have been. Okay, and now I start the simulation, and you see here we have our 460 milliamperes flowing here in our original circuit, and exactly as we have calculated before, in our first circuit we have 20 milliamperes, here we have 400, and here we have 40 milliamperes. So you see the sum here, 20 plus 400 plus 40, leads exactly to our 460 milliamperes.